Hello guys, my name is Ajit Kumar Rana. I am fourth year PhD student from IISc Bangalore. So today we will resume our second tutorial session of the Fundamentals of Spectroscopy. So our approach will be, first we will summarize our lecture slides and then we will solve problem on those lecture slides. So to begin with, let's see the summary of lecture 6. So if we see, let's say we have two states, E1 and E2, let's say we have two states, E1 and E2, and if we see that, let's say we have one molecule here, get is a transition from state E1 to a state E2, and the intensity of this transition, we will say 1 to 2, will be directly proportional to transition dipole moment integral. So I will do 1 to square. And how can we define this transition dipole moment integral? We saw there, we can write here 1 to, let's say we say this psi 1 and let's say we say this psi 2. So we can define this psi 1 is a function of r and t, and we need to write dipole moment and then second wave function. So we saw those things in lecture 6, and we also saw, like, initially if the molecule is not interacting with light, if the molecule is not interacting with light, then we saw that Hamiltonian was H0. But if we are passing some light has two components there. We saw one is electric, another one is magnetic. Okay. So this is more significant. So we consider here the interaction between electric field of the light with molecule. Okay. So initially there will be no interaction between light, since we are not passing any light. Once we are pass some light, the molecule will interact with electric field. It will give rise to some potential V, see, T greater than 0, and this will lead to our Fermi golden rule, and from this we can find, let's say we have two states 1 and 2. As we draw here, we will say here 1, sorry, we will say this is 1 and this is 2. So people can ask, what is the probability of finding in a state 1, in a state 2? So those things we can determine from this equation, this coefficient. A square of coefficient will represent probability of system in being state I. This I can be 1, 2, 3, anything. Okay, so these are the things we studied in lecture 6. So let's see the problem based on this. So this is this question we have. So a function, molecular wave function is psi 1 phi 1 plus C2 phi 2, and the question is asking the probability of finding the system in the state phi 1. Okay, so just we are studying the last slide, sorry, the coefficient of the wave function, the square of the coefficient of this wave function represent the probability of finding in step phi 1. So asking in 5 1, so means the coefficient of sin square. Okay, so this will be the correct choice. People can ask probability of finding in state phi 2. Okay, so in that case you have to take coefficient of c2 square. Okay, the coefficient of that wave function, correct? So if I'll give you some wave function, let's say 1 by 2 under root 2 phi 1 plus 1 by root under root 2 phi 2. Okay, this is the normalized wave function. This is normalized wave function. Okay, if I ask you what is the probability of finding in state phi 1, so how can you calculate that? Probability is coefficient of square, correct? So 1 by root 2 square is 1 by 2. Also one thing to be noted here, so if you write this function psi c1 phi 1 plus c2 phi 2, initially this will be 0, correct? So our resultant wave function will be c1 phi 1. This coefficient will be 1, correct? So in that case we will have psi equal to 5, ground state wave function of the molecule. Okay, so based on this analogy we can calculate the probability of finding in a state phi 1 phi 2, or what will be the initial, or what will be the probability after time t, all those things. Okay, let's see second question. Okay, so we saw there that electric field of the light interacting with molecule, correct? So you have electric charge q, let's say q, so the dipole moment of the interaction can be given by minus q dot e, correct? It will give rise to some potential v, correct? Because of this interaction between the electric field with the molecule, we will have some interaction potential, and the resultant Hamiltonian will be Hamiltonian at 0 plus this interaction potential between the electric field of the light with the molecule. Okay, so what this potential is doing, this potential is causing perturbation in the Hamiltonian of molecule. As a result, the Hamiltonian is changing from H0 to H0 plus 3, correct? So this will be our correct choice. Which one? The first one. Now I'll go to another question. So these are the two questions from lecture 6. So from lecture 7, from lecture C, we saw how the intensity is depending on transition dipole moment, and how this coefficient is giving the what we call the probability in a state I. Okay, so we know that this condition, okay, at t equal to 0, at t equal to 0 we have a1 equal to 1 and a2 equal to 0. But what at t equal to t? Okay. At t equal to 2, using this Hamiltonian and considering the wave function, considering interaction of interaction of electric field of the light with the molecule, and we solve the Hamiltonian Schrodinger wave equation, that is I h cat d psi by psi. We solve this equation and we found this coefficient a2. Okay, and to find the probability we need to take a square. Okay, so this complex conjugate with normal, we get some a2 square, and if you do a square, the square of this whole thing, we will find this mu z square. This is transition dipole moment integral, and the second one is this term. Okay, so this term like I is simply like I theta minus 1 square. So this is like, you can write simply sin square theta by 2. So if you plot this equation, this like I would say like if you plot this equation, you will get some this kind of curve. So what this curve represent? At this point the intensity is maximum. Okay, this is the corresponding intensity. When the intensity will be maximum, when the energy difference between two states, that is E2 minus E1, is approximately equal to h nu. This is called Bohr condition. So at this condition only, this intensity will be maximum. When you will deviate from this condition, why? Because this whole difference will be very small, correct? And when you divide with very small number, you will get very high number. So that's why intensity is maximum at this condition. Any other point than this, you will have lower intensity, like you can see here. Okay, so these were the summary of lecture 7. So we will try to solve some problems based on this. Okay, so if you see here, what the question is asking, the probability of a light induced transition from one state to another of a molecule is directly proportional to. So the probability is like a2 square, correct? So we saw it depends on transition dipole moment integral, state 2 to 1, and the second term was the energy, some exponential term, correct? I am not writing this exponential term, exponential terms. It does not depend directly on the energy difference. See, energy difference is coming on the exponential term and in the denominator, correct? So based on this available option, we can select here this option, the square of dipole, not dipole moment, not wave function. This wave function simply can be overlap integral can be given by this. Okay, energy difference between two states, that's correct, but it's dependent exponentially also, so we cannot set this directly. A square of transition double moment integral associated with two states, this is correct statement that we can see here. This term, this probability is depending on this term. Okay, and the second question, see, solve this question. This same similar question, I think both are, no, this is different. The light induced transition from one state to another is most intense. See, we discuss here, let's say we have two state E1 to E2. Okay, and we draw the analogy here. Okay, we'll have this kind of, and this maximum intensity. Okay, so when the energy difference delta E, that is E2 minus E1, is closely equal to h nu, we call this Bohr condition. Okay, in that case the denominator of that equation, previous equation that we wrote in the previous slide, will be minimum, so the probability will be very high, and that probability is directly related to intensity. Okay, so at that point intensity will be highest. So this is your E2 minus E1 close to h nu. Okay, so what is the correct option? The energy associated with light equal to energy of the ground state. The energy associated with light is much greater than energy difference between two states. No. So this thing you can plug and check from previous equation. The energy associated with light is equal to energy difference between two states. Correct. This is called Bohr condition. Bohr condition. Correct. So we saw here the qualitative treatment, like how the molecule is interacting with light, how the molecule is interacting with the electric field of the light, and how from here how we can calculate the probability in a state 1, a state 2, or in a state I. Okay, what happened in the beginning, what happened after time t. Okay, now we will see how the absorption spectrum we can get quantitatively. Okay, so we see here summary of lecture 8. There we saw like light matter interaction. There, here we are doing quantitative treatment, and for that we need Beer-Lambert law. So what is Beer-Lambert law? So let's say you have your sample here. Sorry, let's say your sample here, length L. This is length L, and we are passing some light with intensity I naught. So it will be constant before entering that sample. Okay, once it will enter the sample, the intensity will decrease, and it is the intensity of light transmitted through the sample. Okay. In the sample we have two things, solute plus solvent, and this solvent is transparent. Okay, what is the meaning of this? This solvent will not absorb any of the light, so all the light is being absorbed by the solute molecule. Okay, so in that case the absorbance is given by this expression, log I naught by IT. Okay, and if you there we solve the equation, we got this absorption equation, A naught is epsilon Cl, where this is called molar extinction coefficient, which is given by Bn 2.3 vacuum, and this B is related to Einstein coefficient. So you can see here that the Einstein coefficient we saw in the first session, that directly relates to your transition from state 1 to a state 2. Okay, so from this absorption equation, from this absorption experiment, we can calculate this Einstein coefficient. Okay, and we also saw like transmittance. This transmittance, how you can calculate this intensity of transmitted light divided by initial intensity of the light, and further we calculated the percentage of the transmittance. It is 100 by transmittance. And how this is related to each other we can calculate here. See, absorbance is given by log of base 10 I0 by IT. So we can write here minus log of IT by I0, and this is nothing but T. Okay, so it will be like minus log of T. So what will be your T? 10 to the power minus J. We derived this kind of expression in that lecture. Okay. Now let's try to solve some of the problems based on these equations. Okay. The first question is aqueous KMnO4 solution is purple in color and given that it follows Beer-Lambert law. A plot of absorbance against concentration is, so let's say we have Q head. We use Q head for absorption spectrum recording. So you have, this is quartz glass, quartz. Okay. So you have KMnO4 solution. KMnO4 solution. And whenever it will follow Beer-Lambert law, this absorbance can be given by epsilon CL. Okay. So if you want to plot using this equation, mx plus c near 0, we plot against concentration. So we get something like this. A, C, a straight line. Because the C slope is 0, sorry, intercept is 0. And what is the slope? Slope is epsilon TL. It's a positive gradient. You can see here, positively increasing. Both are positive axis. This is also positive. This is also positive. Correct. So this will be our correct choice. Okay. So the next question is, we have a cell. So we will draw first cell here. Okay. And we have some solution here. We have some solution here. And the length is 1 centimeter. Length is 1 centimeter. Okay. And what is given? This L is 1 centimeter. And absorption coefficient, that is molar extinction, equivalent to molar extinction coefficient, is given 4 decimeter cube per mole per centimeter. And what is concentration? 6.98 10 to the power minus 5 mole per decimeter. We don't need to change any of the unit because all the units are given in centimeter decimeter cube per mole. So we don't need to change any of the unit. So from this value we cannot calculate transmittance directly because transmittance is defined as IT by I0, or transmittance is 10 to the power minus A. So these information we don't have, correct? But from this information we can calculate absorbance. How we can do that? Using Beer-Lambert law. A equal to epsilon CL. So that is a decimeter cube per mole per centimeter multiplied by multiplied by 1 centimeter multiplied by 6.98 into 10 to the power minus 5 mole per decimeter cube. So this will be cancelled out. Okay, first we will deal with unit. and then this will be cancelled out, correct, and this will be also cancelled out. So what is unit of absorbance? What is unit of absorbance? Unitless, because we are taking ratio. Okay, so that's why absorbance is always unitless. So if you solve this equation, what will you get? You say 40 10 to the power 4, so you will get something 0.698. Okay. Now transmittance is 10 to the power 0 minus 0.698, that is approximately 0.3. Okay. But here the question is percentage transmittance. Percentage transmittance, that is we write TP, which is 100 into T. Okay, so 100 into 0.3, that is 30%. Okay, this one. So if you have this absorption coefficient, this concentration, and in 1 centimeter cell, then your 30% of the light is transmitted. Let's say here you are passing some 100% of the 100% intensity light. Okay, and after passing you will have 30%. Okay, this is your transmittance. You will have 70%, sorry. Mm, 30% is transmitted, so you will have 30%. Okay, so rest of the 70%, the rest of 70% was got absorbed, correct? So we'll solve next question. If solution transmit 50% of the light, transmit 50% of the light, okay, what is the value of A? So what is given here? Percentage of transmittance. What is given here? TP. Is that 50%? From here we can calculate transmittance, that is TP by 100. And why to calculate TP? T, because we saw in the previous slide as well as summary of this lecture also, the absorbance is related to transmittance as log of T. Correct. So if you can calculate this transmittance, then we can calculate the absorbance. So here we'll have 50 by 100, so like 0.5. So what is the A then? A is, we can write as the Dale equation, I0 by IT. Okay, and we can write this minus of log IT by I0, and this is nothing but your transmittance, correct? And we got transmittance here. Transmittance is given 50%, so percentage of transmittance is 50%, so your transmittance will be 0.5. So we plug here 0.5, and we can solve like this: 5 into 10 to the power minus 1, that is minus log 5 minus log 10 to the power minus 1. So it is 0.6, around 7 plus 1. So we are getting something 0.3. So this is the correct answer. Correct. Now I'll go to the next question. Okay. So there we saw some interconversion. Okay. Like we can plot in the incoming slide. We'll see like absorption spectrum. We can plot against wavelength or frequency or wave number. Okay. But before plotting that, you should know how to convert this, how to convert wavelength to wave number, or how to convert wavelength to frequency. Okay. So in this question, it's like conversion. So we have given wavelength 400 nanometer. Okay. So how this wavelength is related to wave number? So it's asking centimeter. So first we will convert this in centimeter. 10 to the power 7 minus 7 centimeter. Correct. And we know that this wave number is inversely related to the wavelength. Okay. So we can write here 400 10 to the power minus 7 centimeter. So it's a 10 to the power, I will write something like this, 4 by 400. So nothing but 2.5. So you have 2500, correct? So this will be your correct answer. Similarly, people can ask you calculate the energy for this, then we can calculate like h nu, and we know that nu is c by lambda, so energy we can calculate hc by lambda. So using this equation 1, equation 2, and this equation 3, and one is equation 4. Okay. We can interconvert this thing. Okay, like wave number can be converted into the wavelength. This wavelength can be converted into the energy. This wavelength can be converted into the frequency. This frequency can be converted into the energy. Okay. And these are very important to know, because in a spectroscopy when you will read, sometimes you will plot against wavelength, sometimes you will plot against wave number, sometimes you will plot against frequency, and you need to know why you are doing that. Okay. So you'll see in the incoming slide. Okay, and there we go. The summary of the lecture is the absorption spectrum that we are getting from Beard-Lambert law. We can plot against wavelength, correct? And this we call lambda max. Why? Because at this wavelength the absorption is maximum, correct? Maximum. You can plot absorption against frequency. So this is frequency, and this is your wave number. Okay. And we saw in the previous slide how can we interconvert these two things. Okay. So the next question will come, how to decide which one to use. Okay. The x-axis, that is lambda or nu bar, should neither be too small or too large. Okay. What is the meaning of this? Let's try to understand this with the help of a numerical. For example, let's say for your spectrum, the lambda you are using is 10 to the power 7 centimeter. It's a very large number. See, when you will convert in the wave number, it's 10 to the power minus 7, which is very small number. But when you will convert this into the frequency, you will get something like 3000 per second. This is a reasonable number, a small number. So in this case, you should use this, not this. Okay, because lambda is very high, wave number is very small, and the x-axis will be like, you need some value which is not very large, which is not very small. You can plot that, but for like simplicity, we do not use very large or very small number. Okay, for our simplicity. Okay, for example, For example, electronic spectrum, we use lambda. Okay. For Raman spectrum, for IR spectrum, we use wave number. Okay. So in the next week, when we'll deal with this spectroscopy, rotational spectroscopy, vibrational spectroscopy, electronic spectroscopy, there we will see the uses of this one. So that's why we need to know how can we interconvert between one unit to other. Okay. Now if you see what is the, now coming to the spectral width. So what is the spectral width? Let's say we have two energy level, E1 and E2. The energy of a state E1 is the E1, the energy of a state 2 is E2. Okay. And one molecule is, when you're giving energy, some energy, okay, some H nu 1 2, the molecule is getting transition from state 1 to state 2. So I'll say this is state 1 and this is state 2. Okay. So there is a energy difference. Okay. So corresponding to this energy difference, we will have fixed frequency. Fixed. Correct. So we should get some spectra where the intensity at any other frequency it will be 0, and at this frequency will be maximum, a single line. But in actual scenario we are not getting this. We are getting something like this. We are getting some broad spectra instead of sharp line. Okay. So this one we can deal using line shape function. Okay. Line is broad, line is sharp, line is too broad, line is too sharp. This thing we can deal with line shape function. So, and why this broadening happening? This can happen because of many reasons. Let's say you have some solution of, let's say, KMNO4. Okay, so you're getting spectra. Say MnO4 is interacting with water molecule. Let's say you have solution in water. Okay. So let's say you have 1000 MnO4 ions. So the every ion or some group of ion will experience different water molecule compared to some other group of H2. So because of that, the energy level may change and you will not get a sharp transition. You will get some transition here, some here, some here, some here, some here, and that will give you a broad peak. Okay. The next question is coming. What are the types of spectral broadening then? There are two types of spectral broadening. One is homogeneous broadening, one is inhomogeneous broadening. Okay. And this homogeneous broadening can be dealt by Lorentzian line shape function, and inhomogeneous can be dealt by Gaussian. So here we understood why the spectrum is getting broad from the lecture, recorded lecture also. There you should watch this lecture and there you will understand better. Here I am going briefly because we are solving problems. Okay, so basically we summarized here. And this Lorentzian shape function can be given by this equation. So 1 by pi gamma nu minus nu naught plus gamma square by 4, and this gamma is nothing but width. Okay. You have Gaussian, if you have a Gaussian line shape function, sorry, then in this case you can given by it can be given by 1 by sigma under 2 pi e to the power minus nu naught by 2 sigma square. Okay. And if you try to look at one absorption spectrum, this is absorption spectrum. Absorption spectrum. So you're getting something like this. This is at nu naught. Okay. And at this point you will have highest absorption or absorption intensity, or you can simply say peak intensity. But to represent the width of this spectral broadening, line broadening, we use FWHM, that is called full width at half maximum. So this is maximum. So this will be your half maximum, correct? So this will be your half maximum, correct? This. So the distance between these 2 points, the distance between these 2 points is called full width half maximum. The first letter of this alphabet. This words. Okay. If you take the difference between this middle and the last line, or this line, we call this half width half maximum. In the lecture slide, professor solved these equations there to get this full width half maximum. It was, he got 2 sigma under root 2 ln2. Okay. So this is your full. So what will be your half? This will be by 2. Full width half maximum by 2. Correct? Because the spectrum is symmetric. We're considering the spectrum is symmetric. Okay. So we'll come this to later. First, based on this broadening, how can we calculate this full with half maximum broadening, half with full maximum, half with half maximum broadening? What is the significance of this? Why we are getting broad spectrum? We understood these things. Okay. So let's try to look on some problems based on these concepts. Okay. So homogeneous broadening is given by which type of line shape function? Is homogeneous is Lorentzian. It's a direct based question. Okay. And that was given by f nu minus nu naught equal to, I forgot the equation, I will check there. Yeah, 1 by pi gamma mu minus nu naught square plus gamma square by 4. Yeah, correct. This is Lorentzian line shape function. One example of homogeneous broadening is gas at high pressure. The second question is how the spectral broadening, this nu naught, here this is frequency of the transition, is related to lifetime of a molecule. To see that, we can write this Heisenberg uncertainty equation like this. T is approximately equal to h card. So we can write this delta E h card by delta T. Okay, and this is related like h card by, we'll write here we'll write here h by 2 pi delta T, because h card is equal to h by 2 pi. This will be cancelled out. I will consider this approximately This is your time scale. Okay, so we are seeing this specular broadening is inversely related to this time scale. You see, if the time scale is very small, this will be sharp. This time scale is large, this will be broad. Okay, so inversely proportional. Shorter time scale related to broader spectrum. Lifetime. Okay, broader spectrum. Correct. This is our correct choice. Okay. Now let's look at another problem. Okay. So this is, we know, transition energy for ultraviolet radiation is more than microwave radiation and transition. So energy for of ultraviolet transition. I will assume this E1. Okay, it's delta, but I am assuming E1. Similarly for microwave, I am assuming this E2. And given here E1 is greater than E2, and we know that this time scale is inversely related to mu. That is inversely related to E, because both E and delta nu is directly related, directly proportional. Okay, so higher the energy difference between two energy level, okay, this one I will say E1 and this one I will say E2. So higher the energy difference, lower will be your time scale. Okay, so the energy for the transition in ultraviolet transition is higher compared to microwave transition. Okay, so the time scale for ultraviolet transition will be lower than microwave. Okay, so UV will have shorter than this. Correct. Now coming to the next question. Okay, similar question we can directly see there. So, we can write here this one, and tau is approximately h car, and this tau you can write here h by 2 pi delta u. Correct. Heisenberg uncertainty principle. Okay. Now we have three. The question is select the order of time scales, that is rotational, vibrational, and electrical spectroscopic transitions. Okay. So we have three energy levels. So one is rotational. If you see the electromagnetic spectrum, electromagnetic spectrum, here we plot something like this. So this way we plot get lambda, and this way we plot frequency. So if you see this line, not this one, electromagnetic spectrum. Okay, so there we saw like the microwave come here. I'll say I am not writing the exact range. So you see this electromagnetic spectrum, and then this IR, and then this UV. So you see the range. This is, I will write UV, this is IR infrared, and this is microwave. So there are three spectroscopic transition. One is rotational, one is vibrational, one is electrical. Okay. So what the energy level, if you draw the energy level, this one, okay, for rotational we have a smaller gap, for vibrational we have higher, and for electronic we have further higher. So this gap is increasing, delta E is increasing, correct? So that's why for this rotation we need microwave, we need microwave, and vibration is comes under IR, and here electronic or electrical, whatever, electronic transitions. Okay. This is your gap. Physically we can understand that, let's say you have carbon dioxide molecule, okay, the shape is linear, let's say this is your x-axis. To rotate along this x-axis rather than to stretch this bond and to compress this bond, the energy for this rotation will be lower than stretching the bond. So that's why the energy gap for vibrational is higher than rotational. In case of electronic, let's say you have CO2 molecule and you have some, let me change the color, you have some pi, 2 pi star transition. Okay, so you are moving here. So basically you are changing the electronic state of the electrons. Okay. So the energy gap between this electronic state is highest compared to this stretching or this rotation. Okay. So physically we can understand like this. Okay. And once we understand this energy difference, even if you don't remember this electromagnetic spectrum, if you don't know this table at all, if you don't know this rotational spectrum comes under microwaves, or vibrational comes under IR, or this electronic comes under UEVs, if you don't know at all, by simply understanding this analogy we can understand the delta E. Okay, I'll say this delta E1, delta E2, delta E3, this is greater. And we saw in the previous slide as well, this delta E is inversely related to time scale, correct? The time scale I will write here, T3 will be greater than T2, will be greater than T1, correct? So we do the correct option, first option. Understood, right? No? Okay, if there are no question, then I'll assume you guys understood this. So I'm moving ahead. So we'll have one more question and then we'll solve some one additional 1-2 question, then we'll end this lecture. Okay, so in case of sample dissolved in liquid solvent, so let's say we're considering this example, we have liquid. Okay. So let's say we are dissolving, sorry, I'll go in listen more. Yeah, we're here. Let's say we are dissolving some KMnO4, okay, KMnO4 solute, or let's say we are dissolving some Werner complex, CONS3 and 6, sorry, Cl3. We are considering this one, okay? In water, we are considering this water. Okay. So when you will dissolve this KNO4 in water, it will dissociate like this. KNO4 solid, and it will dissolve, it will dissociate like K plus aqueous plus MnO4 minus aqueous. Correct. So at the wall of the, let's say at wall of container, we have some MnO4 minus, okay, and it is interacting with H of water molecule because of the electronegativity difference between these two. So it will interact like this. So I'll directly write H2, okay, OH2. Let's say it interacting with 3 molecule, and at the middle of the container of the container, let's say it's interacting with 4 molecule. So one here, one here, one here, and here. So I'll highlight this. This. So this one, and I'll say this. This is I'll say 1. This is I'll say 2. See, environment. So I'll write solvent environment. At 1 not equal to solvent environment at 2. Correct. So because of this solvent environment, the absorption spectrum of this species and this species, the energy gap can be different, and because of that it will lead to inhomogeneous broadening instead of sharp spectrum. Yeah. So this is like different solvent environment of the solid molecule. Yes. So here let's stop this lecture and we'll begin from next session. Okay. So we stop the recording.